Okay, hello everyone. In this video, I would like to show you how to create a very simple model of soil infiltration and percolation. It's going to be a one-dimensional model. What you see on the screen is the diagram of the model, or the schematic of the conceptual model, so to speak. So we have this one-dimensional soil column. I'm going to assume that the cross-sectional area is 1 square meter. It really doesn't matter. You can use a different area depending on your application. We assume that the depth to groundwater is 2 meters. So the groundwater table is 2 meters below the ground surface. And basically what we do is that we will model the groundwater table as a fixed head boundary. Then we have some, so basically what we're going to do is that we're going to discretize our soil column into 10 layers, each of them having a depth of 0.2 meters. You can also do this non-uniformly, but it's going to take a little bit of time because you have to enter the soil properties probably manually. What we're going to assume is that we're going to assume that our soil is sandy loam. So I got these soil Van Genekten soil retention parameters from a source. So we have the residual moisture content theta R, saturated moisture content theta S, saturated hydraulic conductivity, the Van Genekten parameter N, and Van Genekten parameter alpha. So with that, let's start creating the model. So this is my OpenHydroQual window. I'm going to expand it a little bit so that we can see things better. The first thing I'm going to do is that I will basically I have to import the soil unsaturated soil plugin. So what I will do is that I'll go to File, Preferences. I click on Add Plugins, and then I look for unsaturated soil, which is this one. So I'm going to add the unsaturated soil plugin. Now, what happens is that will give me a few components. One is my variably saturated soil block, and then some connectors. For example, soil to fixed head connector, vertical soil to soil connector, horizontal soil to soil connector, which we're not going to use, and then we have surface water to soil connector. So what I'm going to do is that I'll create I'm not going to create my soil basically blocks one by one, even though I can do it, but it's easier to create an array. So what I will do is I'll just go to this Add Objects, and then I click on Create a 2D array, even though we're going to create a 1D array, but we can still use this tool. So what I'm going to do is that I first have to select my block type and the link type. So the block type is, of course, the type of the blocks that I'm going to create an array of, and the link type is the links that will connect those blocks to each other. So I'm going to pick variably saturated soil block as my block type, and then I'll use the vertical soil to soil connector for my link basically type. And then what I will do is that I'll say the number of grid cells in horizontal direction is 1, because my model is going to be one-dimensional. The number of grid cells in vertical direction is going to be 10. Then I click on Next. So then now I have to provide some properties. So let me expand this window so that you can see all the information that we need to enter. We can skip some of these values. So so what I'm going to do is basically what you see here is 3 columns. So actually 4 columns. One is the label. Basically these basically show the property names, and then we have a value. That's the base value. Now in some circumstances I may want the values to be incremented, and we have a for example in this case what I want to happen is that my basically bottom elevation of these soil blocks are going to be different, are going to be incremented in vertical direction. Or you may have a case where you know that, for example, the saturated hydraulic conductivity is linearly increasing. We can still use that. So basically what we have is that the third column is the horizontal increment. That actually indicates how much a quantity will increase at each increment in horizontal direction, and then we have one for vertical increment in our column number 4. So now let me go back to my diagram to get the parameters. So what I have is, let me move this a little away so that I can see the value. So as you can see, what we have is so let's go one by one. The saturated moisture content is 0.41. So I'm going to enter 0.41, and there is no increment. I'm not going to increase or decrease the saturated moisture content. So I'm just going to leave these two boxes empty. The residual moisture content is 0.065. So I'm going to type 0.065. The specific storage is used when the soil is saturated, and then you have pressures that are higher than the atmospheric pressure. I'm going to keep it at this value. This X, this is actually just the location that the GUI actually shows our blocks. So by default, it's the center of the screen is 900, and by the way, it may be a good idea to just change this to maybe 700. I'll show you why. But it's really not, what I just did is not really necessary. And then what it is if I had a two-dimensional grid, which I don't in this case, then this X is going to be incremented by 300, let's say, units, basically for different columns. But I only have one column, so this is not going to be used. If I had some evapotranspiration from the soil, I could actually pick it here, but in this case I don't have it. The width is just the width of the blocks shown on the screen, so I don't have to worry about that. The moisture content is this is actually the initial moisture content. So before the simulation start, what was the moisture content? So let's just assign a value. I'm going to assign a value of 0.2. The saturated hydraulic conductivity is basically 0.0608, so 1.0608. The Van Geneken N parameter is 1.89, so I'm going to enter that. The alpha parameter is 7.5, so let's enter 7.5 per meter. By the way, you can choose the units here, but my units, basically the length units are SI, and the time units by default are in days. So the Y is actually, it's basically just the location that the blocks are shown on the screen. And as you can see, there's a vertical increment of 300. So we don't want the blocks to be on top of each other. So we want them to be, basically their location to be incremented. So this 300 is a reasonable number. I'm going to keep it. The bottom area of the soil block is actually 1. That's the area we're talking about. Actually, it's this area. So it's 1 square meter. I'm going to keep it as 1 square meter. The depth of each soil block is 0.2 meters. The bottom elevation of the soil block, so the first soil block will have a bottom elevation of minus 0.2, and then in vertical direction it's going to be incremented by minus 0.2. So what I'm saying is that each block is 0.2 meters below the previous block. The name is actually the name that is assigned to these blocks. The program automatically adds a counter, but I can just keep the name as soil. I think that's a reasonable number. Then what I will do is that I'll go to next. So this is actually just the links don't have any properties. All the properties for soil blocks are taken from the blocks, but basically the only property that we can enter is the name of the names that are assigned to the link objects. So I'm just going to make it a little simpler. So I'm going to call it soil link. That's it. Then now we can have different properties for the links in X direction and in Y direction. In this case, we only have X in one Y direction, but whatever we assign to X, the links in X direction are automatically assigned to Y too, unless we want to change that. In this case, I don't want to change it, so I'm just going to keep it here. So now we are ready to click on generate, and you'll see that the array is created with all the properties that we gave. So let's check some of them so we can see um, the top soil block is the name that is assigned to it is, let's see the name. I'm going to expand this column a little bit. So there should be a property called names, called soil1 colon 1. Okay, and then the next one is called soil1 colon 2, and so forth. The bottom elevation, as we expect, the bottom elevation of the second soil block is minus 0.4, and that's what we expect. The depth of the soil blocks are all 0.2, so all the properties are assigned properly, so we can move on. So the next thing, what I'm gonna do is that I need to do two things. I need to add a catchment to capture the rain, and then we are gonna of course that rain is gonna infiltrate the soil, and then I need this basically fixed head boundary that is going to represent my groundwater table, assuming that the infiltration will not affect the groundwater table. So let's first do the catchment. So I'm going to use this standard catchment. I'm going to click on that one, and by the way, whenever you add a block, it automatically goes to coordinate 900 and 900 on the GUI. So that's why it was a good. So I mean, it really doesn't matter, but I basically assigned this coordinate of 700, the x, to my column, so the catchment is not on that. Now I'm going to move the catchment to the top. Let me zoom out a little bit, so, and then I can maybe yeah, anyways, so so basically this is my catchment. Now I'm gonna do a few things. First of all, first let's add a precipitation. So in order to add a precipitation, by the way, I'm gonna use an example, sample data that I have. I'll put the link to the sample precipitation data basically in the comments section of the YouTube video, so you can download it, or you can actually create your own based on the precipitation that you have. So in order to add a precipitation, I'm going to click on this cloud icon here, and as you see, something was added to my sources. So this is a precipitation object. I'm going to, just to make things simple, I'm going to change the name of the precipitation object to rain. I'm sorry, and then what I'm going to do is that I will just load my precipitation time series data by clicking on this property, precipitation intensity. So I'm going to click on it, and then my precipitation data is saved in this folder. Now yours is going to be saved in a different place, so, but I'm going to just go here, climate data, and then mine is called sampled rain data. So I'm going to open sampled rain data, and you can see the precipitation. So basically, if I right click on the file name and then click on plot, you can see the precipitation data. So as you can see, it covers year 2010, and these are the precipitation intensities. So with that, let me just save my model just in case. So I'm going to save it to soil column example. That's it. So so now let's go and assign some properties to our catchment. So I'm going to click on the catchment, and as for the precipitation time series, I'm going to pick the rain. That's the only precipitation object that I have, so it allows me to pick that. And now there are several properties that they will not play a role in this case, but we need to enter them, because otherwise OpenHydroQual will give some errors and will not run the program. One of them is the Manning roughness coefficient for the catchment. So I'm just going to assign a number 0.01. We don't have evapotranspiration in this case. And then the other one is catchment slope. So let's just assign a number to catchment slope just in case. And then the only thing that we have is catchment area, which we know is 1 square meter. So I'm gonna assign a value of 1 to this. And then the mean elevation of the catchment is actually 0, so the default value is correct. We set our datum to the ground surface, so we don't need to make any changes to that. I don't think we need to make any other changes to any other parameters, but we'll see if there's something missing. OpenHydroQual is going to warn us, and then we can go and enter those values. So let's just so the other thing I need to do now is to connect my catchment to the topsoil layer. So I'm going to use this subsurface to soil connector, as you can see. So I'm going to click on that one, and then I'm going to manually try to connect this to my soil column. So I did it. Now for this connector, again, I don't need any properties, any numerical properties. The only thing that I can change is the name of the object, which I'm not going to do it. I'm going to keep it what it is. So that will take care of our basically catchment. Now the next thing I'm going to do is that I will add a fixed head boundary that will represent our groundwater. So this is a fixed head boundary. By the way, we have two types of fixed head boundary. One of them is time variable, in case we know that the head of the groundwater is changing with time, and we know that the data that represent the variation. We can use that one. In this case, our fixed head boundary will have just a fixed head of -2 meters. So I'm gonna click on this one. I'll add a fixed head boundary. I'm going to place it down here. Then let's just assign some properties to this one. So in this case, the only thing that I need to set is the head. So the head of this fixed head boundary is going to be -2. That's where our groundwater table is. So that's the only property that I'm going to change. And then the next thing is that I will use this soil to fixed head connector to connect my bottom soil layer to the fixed head to allow flow to occur between the two blocks. So I'm gonna just connect them, and basically let's click on the connector, and basically there's no properties, so I don't have to assign any properties to this one. So my model is pretty much complete. The only thing is that if you remember, my rain data covers year 2010. So if I go to right click and plot, you'll see this graph. So what I want to do is that I want to make sure that my simulation period also matches my rain time series data. So what I'm going to do is that I'll go to settings, general settings, and then for the I first have to specify the end time, because OpenHydroQual will not allow me to enter a start time that is later than the end time. So I better first change the end time. So what I'm going to assign for the end time is January 1st, 2011. And then for start time, I'm going to say January 1st, 2010. So our model should be ready now. What I'm going to do is that I'll just run it. So I just save it, and then I go to this menu, and I look for this gentleman who's running, and I click on that, and the simulation starts. So it takes a little bit for the simulation to complete, but it's quite fast relatively, because our problem is pretty simple. So it took me actually 18 minutes for the simulation to finish, and now I should have some results. So now let's look at the results. So the first thing, I can just right click on any of the soil blocks. So let's, for example, right click on this soil block, and then we can go to results. So these are the results that will be provided. We don't have any evapotranspiration. We can look at the storage. That's the total amount of water in the block. We can look at the moisture content. So this is going to be the moisture content. So anytime it rains, the moisture content goes up and then it goes down. Our soil is quite permeable, so the moisture content is basically doesn't go to saturation because the soil drains pretty quickly. We can look at we can see if any ponding happened on our catchment. So we can look at the average water depth, for example, on our catchment, and as you can see, it's 0 throughout the time. So that means all our precipitation actually infiltrates to the ground during that year. Um, we can look at the precipitation time series, of course, which we've also already looked at. We can look at, I don't know, the flow, for example, let's say from soil layer 3 to soil layer 4. I can, if I right click on the link, I'll see basically in the results, I see a bunch of properties. I can look at the flow. So this is the flow that occurs between block 3 and block 4. We can look at our groundwater recharge, how much groundwater recharge happens. So basically this is our basically link to the groundwater. So let's look at the flow here. As you can see, initially there's a little negative flow. That's because of the capillary suction of the soil. So initially the soil block was drier than the groundwater. Of course, you had a little bit of upward flow, but after that you'll have flow being basically downward throughout the simulation. And that's pretty much it. You can look at other things. I don't know, effective, for example, uh, effective moisture content, which is between 0 and 1, pressure head, hydraulic head, things like that. So if I look at the pressure head, I should see some negative numbers, as you can see, and so on. So now next thing, what I'm going to do is that I'll just add one tracer. I want to basically model the transport of a tracer. So let's just add a water quality constituent. So what I'm going to do is I can basically add basically here chemical constituent. So if I click on this icon, it shows a beaker or something, it'll add a constituent for me. So let's just call, I don't know, let's call this constituent PCB, for example, just so that it has a name. So we have this PCB. Then what I can do is that what I'm gonna do is that I'll assign it to my soil. Let's say our soil layer 3 was contaminated with some 1 milligrams per liter of PCB initially, and then I want to see how long it takes for it to get to the groundwater, or whether we'll get to the groundwater, and so on. So here we're gonna assume that the PCB is completely soluble. So maybe PCB was not the right choice of pollutant, but you'll get the point. In this case, basically the pollutant will be transported with the same speed as water. So what I'm gonna do is now since I added this constituent PCB, I should see a property added to the properties of my soil block, and that's called PCB concentration. So here for my soil block 3, what I'm going to do is that I'll just assign a value of 1 gram per cubic meters of PCB, and that's pretty much it. Now I have this constituent added to the model. I'm going to save this, and I am going to run the model again. So this time it may take a little longer because we have the transport too. So I'm going to wait for the simulation to finish. And now it's done. It takes a little while for the outputs to be written. onto the hard drive. Okay, and then it's done. So now let's look at the concentration. So now I can look at, let's look at the concentration of PCB in our soil layer 3, which was the source. So I'm going to right click. If you look at the result, you see you see these two items added: PCB mass and PCB concentration. I just click on concentration, and you see that concentration starts from 1 and then it goes down as it's being diluted by the new incoming water. I can look at let's say my soil block 9 and see how what's the breakthrough curve of PCB. So I can look at PCB concentration here, and you can see that the PCB front arrives and then it goes back down. I can look at the mass flux of PCB into the groundwater. So if I click on this link, it's a little hard to pick the links, I guess. You know, if I move this away, that'll be easier. So I click on the link from the soil 10 to fixed head 1 and look at the results. You'll have this PCB mass transfer. So you can look at the mass transfer. This could be grams per day. So this is the mass transfer of PCB into the groundwater. And that's pretty much it. Look for my future videos and make sure to subscribe to the OpenHydroQual channel. Thank you for watching.